Hello, and welcome to another video demonstration of SimWise 4D. In this example, we'll look at some of the basic essential elements in SimWise used to create both a motion and FEA model. We'll look at things like grouping parts into subassemblies, adding chords and constraints, motors, friction on a joint, driving the mechanism with test data from a spreadsheet, and creating stop controls to pause the simulation after a certain amount of time. We'll also look at setting up and solving both a static and quasi-static FEA using information calculated from the motion simulation. In this particular example, we will be using neutral geometry from an ACIS type format. For other options in using SimWise, in particular, using SimWise as a plugin with your favorite CAD system, please check out some of the other videos on our website. Let's go ahead and get started. Here we are inside the SimWise interface. We'll go ahead and we'll choose File, Open, and we have an ACIS type file waiting for us, or an SAT extension. If we look at the File Open menu, we can see that SimWise also supports many direct read formats. If you're not using a plugin through a CAD system such as Solid Edge, Onshape, or SolidWorks, you can still read in many different types of formats to SimWise directly. Notice also the neutral file formats that SimWise supports as well. We'll go ahead and we'll double click this file to read it into SimWise. And there we have our model. We'll go ahead and do a couple things before we get started with building the model, and that is we'll turn off the perspective view mode, and then we'll find a spot that looks like a good home position for the model, and then we'll press the S key. That will set the home position. So now if we're ever in a different orientation and we wish to get back home, we can simply press the H key. We'll go ahead and we'll also turn off this global axis indicator here. We're not going to be using that for any reason. We'll turn that off. Now we'll go ahead and we'll begin by grouping our parts into subassemblies. Notice how we have the bodies listed over here in the browser, but there's no subassembly structure, there's no constraints or anything in the model right now. If we had brought this model over from a CAD system using the plugin that I mentioned previously, then we may have subassemblies in here. They may be rigid, they may be flexible. We may also have different constraints that were automatically mapped from the CAD model to SimWise. Since we're using a neutral file format and we do not have any structure just yet, we'll go ahead and begin defining our own subassemblies. I'll go ahead and I'll click, hold, and drag my mouse to grab all the parts in my selection window. And then I'm going to rotate this, and then I'm going to press the Control key, and I'm going to deselect parts that I do not want in the subassembly. That's what we're going to do next. So you can see that we have these bodies highlighted in the browser. We can go ahead now and choose Insert Subassembly, and we'll name this the shaft. And now you can see in the browser that those parts have been grouped under that subassembly. Now we can also right-click on the subassembly name and choose Rigidly Join Bodies. So now all these bodies, including their mass and inertia properties, are included as one lumped body, if you will. So this helps simplify the browser and the motion model quite a bit. We'll go ahead and we'll repeat the process for these slide components here. I'll hold down the Control key, select the parts I wish to add to the next subassembly, and then I'll choose Insert Subassembly, and we'll call this one the slide. We'll go ahead again, right-click on that subassembly name, Rigidly Join Bodies. This time you can see the constraints that appear. These are the constraints that represent the joining of the bodies in that subassembly. If you look here, you can see these constraints, and if you notice I hover over them, you can see them highlight in phantom on the screen. We can turn off the visibility of those icons if we wish. We can also change the size if they're a little big. So there's many things that we can do for the display settings. Next we'll go ahead and we'll select the roller, the pin, this arm, and this bottom pin, and we'll insert another subassembly, and we'll call this one the arm. Again, we'll go ahead and rigidly join these bodies together. Next we'll go ahead and we'll fix the bodies that are going to be stationary or we imagine that these are attached to other components that we don't have in the model. So we can simply say that they're fixed to the background. So we'll simply hold down the Control key, select all the bodies that we wish to include as fixed to the background. Get these slide components on the top. And now with them all highlighted here, we can simply right-click on any one of the highlighted bodies and choose Fixed. Notice the anchors that appear next to these bodies now. So these are fixed to the background. We can also group these into a subassembly, which might make it a little simpler in terms of cleaning up the browser a little bit, and we'll just call those grounded. And there's no need to rigidly join these bodies because they're already fixed to the background, so that would be redundant. The next thing we need to do is simply add a few constraints in here. Now, as a test, if we wish to see where we stand now with building the structure of this model, we can come down here and we can click the Run button to run the simulation. And then I'll stop it prematurely here by clicking that red stop button. And then click, hold, and drag the playback slider to review the animation. Now, we can see that even though these bodies are subassemblies and they're rigidly joined, there's still nothing attaching these things to these fixed parts. So obviously we need some constraints in here. But we can see gravity is certainly doing its job. If we look over at the orientation indicator in the bottom right corner, we can see a small cyan colored arrow. That represents the direction of gravity, which can easily be changed in the main settings. Now we'll go ahead and we'll begin adding these constraints. Now there are several different ways in SimWise that you can create constraints. I'm going to go ahead first and I'm going to select this button here to open up the object list, and then I'm going to simply select the first rigid constraint in that list, scroll down to the bottom and select the very last chord here. All I'm simply doing is hiding the constraints and chords that are currently in the model. I don't need those. Those are simply created by the program representing our rigid constraints, and just for ease of building these other constraints, I'm simply going to highlight them all, right click on them, and choose Hide. And now those components are hidden. So let's go ahead now and begin creating these constraints. So first of all, we'll need a constraint here. We'll need one over here between this arm and the coupler. We'll need a couple on the bottom representing our bearing connection to the arm pin right here. And then we'll also need a couple that support the shaft to these bearings right here. So we'll go ahead and we'll begin by adding chords. That's one way to create constraints in SimWise. Now chords represent miniature coordinate systems, and I'm going to go ahead and click on the chord tool right here, and it's going to activate a filter. These are miniature coordinate systems that are the basis for all the different features that you'd build in SimWise, such as constraints, forces, springs, and dampers. And the chord is the basis in the sense that it helps attach the feature to a specific body. It defines a location, and it also defines an orientation. As I mentioned, it's a miniature coordinate system. If we go ahead and we click on this circular edge, notice how the mouse cursor changes to a crosshair, and we'll go ahead and we'll select that circular edge, and we've created a chord. And you'll notice there, let me go do this. Let me change the visibility to be translucent, and then click on that chord. Notice the axes that are represented through that chord. So that chord has its own orientation. We can certainly change that orientation. We can do things for chords such as track the position, the velocity, create trace paths so that we can see the trajectory of a particular point throughout the simulation. And so they're very useful. So let's go ahead and let's click the chord tool again, and we'll add the additional chords. I'm going to hover over that circular edge and add a chord there. And then down at these bearings, I'll go ahead and select the circular edge on that block and the circular edge on the block. Even though the pin may be directly attached to the radial bearing, it's okay for us to attach the pin to the pillow block itself because the loads are going to be the same. These are both fixed components, so either way would be acceptable. We'll go ahead and select the circular edge of the bearing. Notice that established a chord right there at the center. We're going to use that in just a moment. also put one on the back side here. And so there we have the chords. I'll simply right click and choose select to get out of the chord creation mode. And now I can begin adding these constraints. So I can simply select the chord, and I know the chord is attached to the bearing part. So we're picking up multiple objects. So we have the chord selected. It's attached to the bearing. So then the other component I wish to attach is the shaft. So I can select the chord just like I did, hold the control key, and right mouse click on the bearing at the same time. And then the shaft. Choose create constraint, and then we can go ahead and we can add something in like a revolute motor and choose create. And there's the motor icon. Next, we'll add a constraint between this bearing and the shaft here. Notice how I can't see the chord very well because it is hidden under these bodies, but if I simply select the bearing, which I know I attached the chord to, and then I look in the connections list, I can see that chord right here, 87 on body 7. And if I hover my mouse over it, you'll also see that chord highlight on the screen. So I can click it, hold the control key, right mouse click the shaft, and then create constraint, and I'll go ahead and put a spherical joint at that location. Okay. Now, you may wonder why I'm adding some of these joint types. For example, why did I not just add a revolute constraint? Whenever you're dealing with any sort of rigid body dynamics simulation program, you have things called redundant constraints. And so we work to avoid those by using different combinations of constraints. That's subject for a later video, but that's the reason for doing that. Now I'll go ahead and I'll click the chord that's attached to the arm, hold the control key, right click the arm there, or this link, excuse me, choose create constraint. I'll go ahead and add another spherical joint. We'll select this chord, this link, create constraint. This time I'm going to add a revolute on slot. And then down here, we'll go ahead and select the chord. We'll select the pin that's attached to the arm, create a constraint. We'll add a spherical joint. You can see that we can add these pretty quickly once these chords are into their proper position. Select the chord, select the pin, create a constraint. This time we'll do a spherical joint on slot. And so we have those connected. Now, one constraint I forgot about was this slide right here. So this slide is actually guiding inside these guide rails here, but the guide rails are fixed to the background. So essentially we could also add a constraint that represents a slide constraint that attaches the slide to ground itself. It doesn't necessarily need to be attached to these blocks if I'm not trying to extract any information from these guide blocks such as stress or force or anything like that, which I'm not. So I can simply add another chord, and I'll come in here to the front of this slide and just click on that face. And if I wanted to position that chord exactly, I could do that. I could just simply double click the chord now, and I can come down here into the properties list and turn on the world position tab, and now I can enter these different coordinates. Just a side note here, these double arrows represent the fact that I can create parameters that control the position of this chord. That's very useful for something like the SimWise optimization that could be run later on. We'll go ahead and close that. Now, select the chord, and since this is attached to the background, I don't need to select another body. The chord is attached to the slide. All I need to do is right-click the chord and choose Create Constraint. And notice here how it says it's going to create a constraint between that body and a new chord on the background, which is what we want. This time we'll use a rigid on slot and create. And there is our constraint. Also note that we have the move tools in here. So if you click on the move tool, your mouse cursor changes to a little hand holding a T block there. You can click, hold, and drag these different bodies so you can kinematically make sure that they're properly connected. I'll go ahead and undo that. Click the move tool again and maybe grab this arm right here. I need to be in a rotated position. Let's try that. And let's try instead turning the shaft and it's not turning for me. There we go. I wasn't selecting the body properly. So you can see that we can verify these connections. This is the same technique that we use in a CAD system. So the difference is here that we can still do these kinds of things like we would in a CAD system, but the benefit we have with SimWise is that we're going to be able to determine all the physics behind the model, which you can't do with the constraints and simple move commands inside a CAD assembly module. So we'll go ahead and reset that. And now if I come down and run the simulation, I can see that we have a motor turning that shaft, and I left the default value of the motor, which is 90 degrees per second. And so that looks really good. We have everything connected properly, with the exception of one thing that's quite obvious, and that is the collision between this roller and this block. It's easy enough to add that if we just simply click the roller, hold the control key, right click on the block, and choose collide. Now those bodies are set to collide. I'm going to come down here before I run the simulation, and I'm going to click on the contact properties item, and that will activate a contact tab in the properties list here, or in the properties dialog. And then I'll click on smooth surface single point. So there are different contact methods and response methods that we can use, and which one we use may depend on the type of geometry that we have. Whether we have simple circular geometry on a flat face, or we have more complex geometry with multiple points of contact, whether the parts are heavy or lightweight, these things make a difference. So we'll go ahead and we'll just use the single point, and then we'll leave the default for impulse momentum, which is also known as the coefficient of restitution. Close, and we'll go ahead and we'll run the simulation. So you can see we have a collision there. And this is different from a tangent constraint that you might have in a CAD system. This is what you might call an intermittent contact. It is defined such that if there's any clearance in here and there's any slop, so to speak, any chatter that might take place, the program will capture that because it's allowed to come in and out of contact, unlike you might have with a tangent constraint. So let's go ahead and stop the simulation, rewind it, and then next we're going to apply a real engineering application, if you will, to this example. Now the goal is to drive this slide using test data that we have stored in a spreadsheet, and then reverse determine what the angular displacement needs to be on this shaft to achieve that same output profile. So essentially we're driving the linear output and reverse determining the rotary input. So to do that, we'll simply control the motion of this using spreadsheet data. So we can double click this rigid on slot constraint that we created, and we can simply change that to an actuator. Once we do that, we can scroll to the end of the tabs and then click on the actuator tab, and then we can click on length displacement for the actuator type. And then I just noticed that before I read in my data, I want to change my units. My data is in millimeters versus time, so we need units of millimeters for our length. So we'll go ahead and close this very quickly. We'll just right click, open the display settings, and then come into the unit settings here. And then we'll change our unit system to actually SI degrees. That'll work. And then we'll choose millimeters for the distance. And then we'll go ahead and close. And now we can double click that constraint again, and notice how it comes right back up under the actuator tab. Now we're in millimeters. Now we can click on this formula button here. This formula button is very useful for many things, and you'll find it in things such as springs and dampers and forces. Typically anywhere that there is a function that you can define or a value field, you'll see the formula builder option. And if we click that, that'll launch this formula builder, which has many capabilities in terms of defining custom inputs, predefined inputs that come with the software, creating slider controls and things of that nature. If you look under the function list, we can see many different curve types that are supported in here, and these are ready to go. So basically you click on a step function, for example, complete the parameters, and then hit OK, and it defines the function for you. You can also create tables out of your own defined functions. So there's many different things that you can do. Under logic, we support these different logic functions. An if statement is a very useful function. We have mathematical functions, and we also have properties, meaning we can use these different property controls to define interrelationships in the model. For example, I might want a force to turn on when a body's velocity reaches a specific value. Okay, so in our case, we're going to read in table data. So I can click on this Insert Table icon, and then I can click on the Open button, and then I have my data waiting, this motion input, and as soon as I read that in, I can see what that curve looks like. And I can stretch this dialog box out a little bit to get a better view of that curve. I can see that we're spanning a time interval of 1.5 seconds. We are in fact using millimeters. And then I have the data over here. If I click and hold and drag any one of these points on the curve, I can reshape this curve, and then I can resave it to a new file if I wish. Another thing to note is that the independent variable here is time. That can be anything you want it to be. For example, we might have a nonlinear spring and damper where we're using force versus velocity. So we could define a velocity function here. We'll go ahead and choose OK. And then notice here, before we OK our way out of here completely, notice that it has this input 78. So it has assigned an ID control to the input curve that we read in. Now what this means is that we can use this input syntax right here. We could even copy it to the clipboard, and we can place it into other functions or meters and do some customization. So we can use that and reference it in different areas of the simulation. We'll choose OK, and then we'll choose Close. And a quick note here, if you come to the Inputs and Outputs button, you'll see that also you have that input showing under this Input and Outputs area. Also, if you start creating meters, the meters will appear in here as well. Okay, so the next thing we're going to do is set a stop control for the simulation time. We mentioned that we read in 1.5 seconds of data, so we'll go ahead and we'll define a stop control that will stop the simulation after 1.5 seconds. We can simply say when time is greater than 1.5. Notice how it has the formula button here, so again we can write many different formulas or define criteria to stop this model or stop the simulation. Choose Close, and then we'll go ahead and we'll run the simulation. Oh, the one thing I forgot to do is I forgot to remove the motor. So we have a redundancy here, and we're trying to drive the slide. At the same time, we're trying to control the motion of the shaft. We don't want to control the motion of the shaft, so we'll go ahead and double click this motor to open up its properties. Click on the motor tab, and then we'll set the torque value to 0, so it has no resistance and it's basically a freewheeling joint in this case. So now we'll go ahead and we'll run the simulation, and we can see that we don't have that motor fighting the motion anymore, and we have a nice cyclic motion, one cycle. We can look down here on the right side and we can see 1.5 seconds. So if we click, hold, and drag our playback slider, we have that one cycle that we read in. Now, if for some reason the data was reversing the direction of what we intended, then we can simply reverse the direction of the actuator by right-clicking on it and choosing the Swap Chords option. And that'll simply swap the X and Y, or excuse me, the plus minus Z directions for this constraint, which would in turn reverse the motion. Now that we have things moving correctly, let's go ahead and let's create a meter that will show us what this angular displacement is of the motor right here. So if we can't see the constraint, which we can, remember we could always click on these bodies and then look at the connections here and select it that way. But the graphic is nice and visible, so we can simply right mouse click on it, choose Insert Meters, and we'll look at the orientation. So there's our meter. Now if we go ahead and run the simulation, we can see what that angular displacement profile needs to be at the motor. So now that that's completed, what we can do is we can simply right click in this region of the plot and we can copy the data and we can basically save it to the clipboard. And then we can read it back in. And let's look at that now. So I'll go ahead and I'll rewind the simulation. By the way, I've already saved this data, so I don't need to do it again. I've saved it into a text file. So I'll go ahead and rewind this. So now that we've got the profile that we need, we'll go ahead and we'll change this actuator joint that we put in here temporarily back to a rigid on slot. Double click it, then we can select the rigid on slot and close, and now that joint is back like it should be. Now, as far as the motor back here, now we need to read in the test data that we just determined and saved and drive the motor with that data. So we can double click the motor, just like we did for the actuator. Instead of an actuator tab, it has a motor tab because it is a motor. So we click on the motor, and we can click on orientation, and we've got the correct units, degrees. So now we can click on the formula button. Just like we did for the actuator, we'll read in a table. And like I said before, I had already saved this previously. We'll call this the motor input. And that is what our data looks like. Again, we just talked about being able to reverse the direction of a motion. You can always insert a negative sign in front of the motion statement itself to reverse it. Or in this case, we can put a -1 times input 82, and that'll reverse it. We could also swap the chords by right-clicking on the constraint. Okay, so we'll choose close. And now we'll go ahead and we'll run this simulation, and I would expect it to be identical to what we just saw before. So now we're driving that shaft instead of the linear slide. So now the benefit to this is not only did we determine what this profile needs to be, maybe we're starting to get some basic information into the sizing of a servo motor, but we can also now load up the mechanism with realistic forces such as external loads and friction, and then we can study the effect that it has on the torque for this motor. So let's rewind this, and let's create a meter for the torque of that same motor. This time we'll do a constraint torque. And we can look at the torque either on the bearing or the shaft. Since the constraint joins both of these bodies, one of them is going to have an equal and opposite reaction to the other. So it really doesn't matter. There will just be a sign difference between the two. We can go ahead, if we're not sure, we can always go back and see the constraints as to which, or excuse me, the bodies, which body is 1 and which body is 8, and then we could choose our torque that way. I really don't care in this situation. They're going to be just the same with the exception of a sign. I'll choose 1, and we'll look at that with respect to the world coordinate system. So there's the meter. So now if we go ahead and run this simulation, now we're getting a Newton millimeter torque plot for the motor. And we can change the readout of this meter as well. So we can go to a digital form, just right click in the gray region, choose digital, and then we can see these values, and we can also show the min and max, which is very handy. So if we drag this back, we can see those numbers change in real time. So we get a basic idea of the amount of torque that we'd need for this. Change that back to graph. Okay, we can also hide these components as well. So if we just left click on here, and I'll undo the TX, I'll undo the TY, and basically I'll undo the magnitude. We're just looking at the torque about the Z-axis in this case, just like we are down here for the rotational Z. So that gives us an idea of how much torque we have on this. Now, like I said, we can begin to apply different loading into the system to study the effect. So in an ideal system right here, we have no friction, no resistance. This is the ideal torque for the system. But that's going to change as we begin to load things up. So for example, if we add friction in on a joint, let's go ahead and let's do that. Perhaps we add friction on this sliding joint. Let's double click it, and then we'll come over here and choose the friction tab. By default it is disabled for all joints. We'll go ahead and we'll enable it, and we'll say maybe 0.2 for the coefficient. Notice also we have the formula builder here. We can customize our friction coefficient. Maybe it's dependent on the motion of a certain object. Maybe it's not your your traditional sliding friction. Maybe we have something more complex. We have some fluid in here, some oil or grease that's creating extra resistance. So let's go ahead and let's just close that. And now if we run the simulation here, we get a new profile. Okay, and we can also create, we probably should have done that before we started the simulation, but we've got a new profile for this. So we can go ahead also and right click on that, insert meter constraint force, and we'll just choose body 21 with respect to world here. 21 should be the slide. But if I run this now, I can see the force on here, and my friction force is going to be along the friction force is going to be along the x-axis of the global coordinate system. And in this case, we can see that that value is approximately plus minus 1 Newton. And the plus minus represents the change in direction. Okay, so now let's go ahead and let's delete the results for this. And let's look at another aspect of this. Let's say, for example, we want to perform an FEA on this on a particular member here, maybe this arm right here. There are a couple different ways that we can do finite element analysis in SimWise. One is to run a simulation like we just did, and then maybe we have some different plots up here and we determine at what point we want to calculate the FEA. So we might be looking at what point the shear stresses and the bending stresses are maximum through the range of motion, and then we can basically stop it at that point. And once we do that, we can right click on this arm and we can include in FEA, and you'll notice something that happened right there. As soon as I did that, I saw these graphical arrow icons appear. What I'm going to do is I'm going to hide all other bodies except the constraints for that body. So I've got the body and the 3 constraints associated with it, and I'm going to simply right mouse click and choose visibility, hide all others. There, we have a better view of that force. So what this represents is this load graphic is the force that's acting on this joint. So we can calculate the forces by creating these different meters, and we can graphically and numerically see what's happening. But the software doesn't understand onto which geometric faces those loads are applied. So what we do is we begin defining the load distribution faces. So for this one, this looks correct. If I hover my mouse over the graphic, I can see this constraint highlight in phantom. So I know I have the correct constraint. So this one is correct. Let's look at these other 2 down here, and I can see that they're turned off right here. So let's go ahead and let's turn on 71 and 74. We'll show those constraints. Okay, now that the constraints are shown, we can see the load graphic. This represents the load for the upper pin to the arm and the bottom pin to the arm. The constraints are made between the arm and the pins, but the software doesn't know onto which geometric faces to apply those calculated loads. So let's start with constraint 71, which is, if I look in the connections list, between body 17, the arm, and body 18, I can see that's the upper pin. When I hover my mouse and I look in the graphics area, I can see it highlight in phantom. So constraint 71 is between those bodies. So when let's go ahead and let's hide constraint 74. Whoops, I had them both selected at the same time, and that's why I hit them both. Let's turn this one back on. Okay, so this is the upper pin to the arm. We can right click on the load graphic, distribute on face, and I can select that cylindrical face. Notice how it applied it on that face. But what about the other side? That's not a problem. We can simply right click on that graphic again, distribute on face, and then if I need to select more than one face, I now hold down the control key and pick the other face. Now you can see that the load for that pin is distributed equally amongst those 2 ears. We'll do the same thing for the constraint for the bottom pin to the arm. I'll turn off this constraint I just had on. I'll turn on the bottom one. And you can see how the software doesn't really know where to apply those load distributions. So it makes an assumption automatically. And in this case, this assumption is not correct. So it's up to the user to make sure that these distributions are assigned correctly. Right-click on the load graphic, distribute on face. We'll pick the bottom face. Again, we need to distribute it also onto this one here. So we right-click the graphic again, distribute, hold the shift key, or excuse me, the control key, and then select the other face. And let's turn 71 back on. So now if you look, we have those loads applied to their proper faces. So I'm just going to go ahead now, I'm going to turn everything back on. Okay, go to the home position. And now that we've got this in the position that we want, let's say for example we're looking at maybe this load situation right here. Maybe we want to investigate what the current status of the stress is. Now we can simply click on the Solve button for the FEA. And this will automatically mesh the part and solve it. So there we have the solved result right there. We can see the default display of the von Mises stress. We can change these stress values by right-clicking on the legend. You can see we have strain and displacement. We also have, say, averaged and unaveraged values, factor of safety, and then your different principal stresses, for example. So we can see the result on that body. Now, there are other things that we can do for this to post-process this body. So, for example, if we just right-click on that body and let's hide all others, we can see what this looks like. Now we can right-click on the body again and we can choose the Show Mesh if we want to see what that default mesh looked like. Not too bad. However, we're not really sure maybe that we've converged on a good solution yet. SimWise has a feature called H-adaptive analysis where the program will automatically readjust and refine the mesh in areas of high stress error. The default value of the stress error is 10%. So let's take a look at that real quickly. If we come down and we click on the H-adaptive button here and then just click on Solve H-adaptive, what it does is by default it's using 10% as the error value. And we can see here that it tries to refine the mesh in the model such that the stress error is below our defined value. So the default value is 10%. We ran it the first time. It made one adjustment. I can see that the mesh is a finer resolution now. And it achieved that goal of 10%, but actually exceeded it by reaching 9.2. So if we'd like, we can change this target error now to something smaller, maybe 6 or 7%. And then we can continue the H-adaptive. And it'll continue to refine the mesh only in the areas that need it. So that's a very useful tool in helping you extract the accurate results from your simulation and from your FEA. So let's go ahead and close this. And I'm going to go ahead and show everything once again. And now let's go ahead and let's right-click on this body and let's uncheck the Show Mesh. And I'm going to go ahead, double-click it, and bring up the FEA tab, and I'm going to delete the mesh. Okay, and the reason I'm doing this, obviously we saw that we needed one refinement to get more accurate results. But the reason I'm doing this is for the purpose of the video demonstration. I'm going to change it back to the default mesh, and then I'm going to run a multi-frame motion plus FEA. So let's go ahead and do that. We'll rewind the simulation, and now that I've got that body included in the FEA and the loads are assigned, we can click the arrow next to the run control and we can change this to motion with FEA. And let's go ahead and let's run it. So what it's going to do initially is it's going to mesh the part and then it's going to solve it for that particular motion frame. And so you can see it slowly moving through this process, solving quasi-statically an FEA for every single motion frame. This is very valuable with SimWise. So it automatically assigns the loads, the load values, and the load directions into those boundary condition positions for the FEA. Boundary conditions are very critical for an accurate FEA in addition to the mesh. And something else we should note here, by default, we're using steel as the material for this. So we could certainly change the material if we wanted to. And we can customize our material database. So I'm going to go ahead and stop the simulation prematurely, and then just click and hold and drag this back and forth a little bit. So you can see the power here that we have in running a motion simulation and an FEA simultaneously. So there's a lot of valuable information here. Along those lines, we can right click on that body and we can choose Insert Meters, and we can choose FEA Result, and we've just created a von Mises stress plot. Now at the beginning here it has to adjust itself and converge on a solution, so it's trying to find its happy medium, if you will, at the very beginning. But then as it begins progressing through the additional range of motion positions, you can see that it has a nice smooth curve, and the stress does start increasing as we begin coming down this way. And I can see that visually on the model as the light blue starts to increase a little bit, and that coincides with this increase in stress that we're seeing on the meter. So very useful feature in SimWise. This concludes the demonstration. Please be sure and check out other videos on our website showing other capabilities of SimWise, including optimization and durability.